Take away one methyl and replace it by H, now there's only one methyl left, that's hotter. So in general, actually, aldehydes are more reactive in these nucleophilic additions, starting with sodium borohydride and Grignards, back to chapter 8. Aldehydes are more reactive than ketones. So you can distinguish between the two by just, if you have an oxoaldehyde of the type that we just did the naming of, that if you fire one equivalent of Grignard at it, it should preferentially attack here. Notice, however, there's a little quirk here. The OH will kill your Grignard, so you have to protect the OH as a T-butyl ether. But otherwise, aldehydes are more reactive. So then you go to formaldehyde, that's more reactive than this, and then when you put electron withdrawing groups in here, that's even more reactive. And so you can see this very nicely, the two extremes in the electrostatic potential maps. Acetone is so greenish blue, it's a tinge of blue, okay, indicating delta plus character. By the way, very different from a CC double bond. CC double bond will be all red, as you may recall from, actually we showed even one picture in the benzene electrostatic potential map, all red. But here, because of polarization, this is now green-blue. But if you go to this guy, now this is really blue, okay? So there is much more plus charge on that carbon, and therefore it's correspondingly hotter. And you can measure this by the equilibrium of hydration. If you start with the most activated one, the least happy carbonyl, it really wants to be hydrated. And so the equilibrium is actually like 10,000 to the right, or more than that, but 35,000 to the right. Formaldehyde, still pretty hot, it's about 1,000 or a few thousand to the right. Okay? But acetaldehyde now, this guy, which has the methyl pusher, is now a little better behaved. That's actually one. So if you were to take an NMR spectrum of acetaldehyde in water, you'd see two species. 50% of it will be the aldehyde peak, and then with one methyl group, and the other 50% will be the hydrate, with the OH peaks and the two methyl groups. Okay? Two compounds in solution in 1-to-1 ratio, roughly. And acetone is so stabilized that the equilibrium now lies to the left. Okay? But in terms of practical consequences, the point is that it's an equilibrium, back and forth. Another point of the practical consequence of this is that it's very difficult to isolate hydrates, because the moment you try to, you can't put them in a bottle because they immediately set up the equilibrium with the corresponding carbonyl compounds. So you can only isolate it when you drive it all the way. So for formaldehyde, for example, in the solution, it'll be the hydrate. So you can try and isolate the formaldehyde hydrate in this guy too. But it's not of any practical significance, so we won't really isolate hydrates. We don't make hydrates. Nobody makes hydrates because they're not stable because of this equilibrium. But they're important as intermediates in chemistry, and the hydration topology, the experiment itself, the reaction itself, is important because we can now generalize from it. And one generalization is to switch to alcohols. And alcohols you can view as alkylated water. So the only difference is one of the H's is now R. They do otherwise exactly the same thing, not unlike what we saw in nucleophilic substitution. Hydroxide and alkoxide were identical in their chemistry. Right? So alcohols add, and they form what's called a hemiacetal. Hemi is Greek for half, and acetal is for a species that comes in when you push this further, such that this OH is replaced by another OR, which we'll do in a second. And if you do this for aldehydes, you get this species. If you do it for ketones, you get this species. Okay? But the essence is the same as with water. The proton goes on the delta minus oxygen here. The alkoxy goes on the carbon. And it's an equilibrium, and the equilibrium constants are essentially identical to those observed in hydration when you look at the variously substituted carbonyl compounds. Now, there's a little quirk, a little aside that will come in here that's kind of interesting, which we've only encountered really once, and that's entropy. In these reactions, two molecules turn into one. Up until now, we didn't care a damn about that because the delta H of the process was so exothermic that whether we went from disorder to order, which is thermodynamically unfavorable, didn't matter. But now the equilibrium constants can be close to 1, and so entropy does play a role. So how does entropy come in? You probably don't remember that, but entropy is a term in the delta G, I'll show the equation in a second, that refers to the degrees of freedom in the system. Nature strives for freedom, okay, which is often translated into disorder. The more disorder the system, the more degrees of freedom, the better. So going from 2 to 1 is actually bad. You see nature in action everywhere, this business of nature strives for freedom. For example, a screw unscrewing itself over time. Or a better example is look at your room. Okay? It's a total mess, and you're totally in tune with nature, because that's what nature wants, total disorder. Okay? And it costs energy to order things. So 2 to 1 is entropically, energetically costly. So why is this important? It's important because when you now do the same reaction, this would be essentially an acetaldehyde, ethanol, with an alcohol, but we're now doing it intramolecularly, where instead of turning 2 molecules into 1, we just turn 1 molecule into 1. Now the equilibrium constant is larger than 1. For acetaldehyde, remember, the equilibrium constant is around 1. Now suddenly it becomes more favorable. Why is that? This is because the entropy term is smaller, because we are generating less order than we did before. Turning 2 molecules into 1 was entropically less good or worse than turning 1 into 1. In both cases, the entropy term is slightly negative. Here's the equation. Here's the free energy of a reaction that is connected to the equilibrium constant. And by far the major term is the enthalpy, which is bond strength made versus bond strength broken. But there's this minus T delta S term. This is typically in kilocalories. Okay? That's thousands of calories. Whereas delta S is typically only in calories. It's a very small number. And for dissociation, 1 going to 2, it's plus 25 calories per degree centimole. But what makes it a little bit more significant is this T term, which is in Kelvin. So at room temperature, that term is roughly 300. But for, if your entropy is plus 2, you multiply this by 300, that's 600 small calories. So it's 0.6 kilocalories. So in most reactions, we ignored this, and we just relied on the delta H, which gave us a good prediction of will a reaction go forward. But there are now cases, and this is one of them, where the delta H is just not that big, such that T delta S comes into the picture. And we won't do numbers. I'm just telling you that the intramolecular hemiacetal formation is now favored, goes to the right. And this has consequences in nature. For example, this is a glucose. Sugars are hydroxyaldehydes. I just mentioned this a little earlier, polyhydroxyaldehydes. And they don't exist in the open chain form. And I lined this up so that you can see what happens. This OH moves in to form the 6-membered ring cyclic hemiacetal. And the equilibrium lies on the side of the cyclic system, to the tune that the aldehyde form is only 0.003%. So there's some real consequences to this scenario and to the intramolecularity of this process. Okay, so now we can drive that equilibrium all the way to the acetals, and that's where the name hemiacetal comes from, because you're going towards an acetal. An acetal is one in which the carbonyl function has been turned into a double ether, a genyl diether. And those actually can be isolated. And that transformation requires acid, and we'll see in a minute why. It goes through the hemiacetal, and we need only acid will take the hemiacetal all the way to this, because in the hemiacetal we have OH, and we have to make the OH leave by protonation, and the carbocation is then trapped by ROH. You can do all this in one pot. Carbonyl plus typically excess alcohol, you need at least 2 molecules. Acid catalysis, the equilibrium constant is now to the right again, and you can isolate this guy. Why is this important? First of all, it's the first reaction of a carbonyl compound, new reaction, where we actually isolate something today. Secondly, this is a great protection of a carbonyl, because the reaction goes back if you treat this genyl diether, this acetal, with acidic water. With acidic water, now everything goes back to that side. So you're basically driving the equilibrium to the right with excess ROH, and to the left with excess water. Why is this good? Again, it's a protecting group strategy, because acetals are stable to base, they're stable to oxidizing agents, nucleophiles. They're stable to Grignard's alkyl lithium hydride. So all the stuff that ordinary carbonyl compounds react with. So if you wanted to do a reaction with a Grignard reagent, say opening an oxocyclopropane at one end of a molecule, and but you have a carbonyl function in the same molecule, you need to protect the carbonyl. And in order to do that, you can turn the carbonyl into the acetal. And the only thing acetals are not stable to is acid, which reverses the reaction. So this is a little abstract, and we'll see some examples soon, but here's the mechanism. And the mechanism is a follow-up on hemiacetal formation. And it's completely identical to what I did here. For acetal generation, we go through the hemiacetal using acid. Okay? So this only works with acid to go all the way. The first line, however, goes with both acid and base, similar to what I did for hydration on the board. So what happens? You protonate first. That activates the carbonyl function. Notice the equivalent, the other resonance form, which is a hydroxycarbocation, nothing else but a protonated carbonyl. We now attack this, and I'm picking this arbitrarily. Okay? Remember, resonance forms are two extreme representations of the same structure. And the true structure is a superposition. So you could attack here, or you could also attack here and move the electron pair out. Either one is fine. And so it traps this to give the protonated alcohol adduct here, protonated ether, the proton falls off. That's the hemiacetal. So that's what we did over here on the top right board with the water. Then we go on. We want to exchange OH for OR, and we can achieve that by protonating the OH that turns red, the nucleophilic O, into green, the leaving group water. The leaving group leaves, you get a new carbocation, now an alkoxy carbocation, for which again we can write a great resonance structure. That's an octet. And that is trapped then by a second molecule of ROH, and you get the protonated diether, the proton falls off, and that forms the acetal. And you can see that this can only work with acid, because the exchange of one OH for another RO can only work with acid, because you have to turn this guy into a leaving group by protonation. If you treat this with base, a hemiacetal with base, you go right back to where you came from, because base will deprotonate the OH to make O minus here, and the O minus will kick out the alkoxide, and you're back to where you came from. So it will only work with acid. Is there a question up there? Yeah. Because thermodynamically you now go sufficiently downhill that it drives the equilibrium. And I should say it's also favorable because you set it up to be favorable by using excess of the alcohol. Okay? So it's still an equilibrium. Your thermodynamics help you, but you're also using excess alcohol to drive the equilibrium. Conversely, if you want to deprotect the protected species, namely hydrolyze the acetal, you use excess water in acid. So now the equilibrium shifts the other way, because excess water will drive it the other way. So this is a new scenario. Okay? The equilibria are such that you can drive in either direction by control of the reaction conditions, something we haven't seen before. So mod is over, and back to preparing for the midterm. I'll let you go. Thank you.